Donc c'est une exposition en fait qui va démarrer dans quelques semaines, qui s'appelle Envie aux frontières du design ou Alive New Design Frontiers. C'est une exposition qui met en scène des architectes, des artistes et des designers qui travaillent en fait avec des technologies du vivant ou bien qui imitent le vivant. Et donc nous avons à peu près 34 projets qui seront présentés, qui vont du design de mobilier à l'architecture, au design de mode, chacun avec une approche très particulière de par leur rapport à la nature. En fait, c'est une exposition qui met en scène un nouveau langage du design et une nouvelle relation à la nature, qui part de la nature, ce que j'appelle la nature naturelle, et qui va jusqu'à la nature synthétique ou reprogrammée. Et nous avons choisi pour cette exposition d'avoir un artiste phare, un artiste qui est un architecte qui est connu mondialement, qui s'appelle Philippe BEESLEY, qui présente ici une nouvelle installation qui s'appelle Radiant Soil, grâce au soutien du Centre culturel canadien et du gouvernement du Canada, ainsi que de la Fondation EDF. Cette installation que vous voyez un petit peu ici, qui est en fait le workshop, l'atelier où on est en train de préparer le montage qui va se faire la semaine prochaine, cette installation est en fait une installation architecturale métabolique qui met en scène plein de réseaux. Philippe parle de nuages en fait, de clusters, qui en fait sont tous interconnectés et qui interagissent, qui créent de l'énergie et qui filtrent l'air. Et ce qui est intéressant ici, c'est l'imitation d'un métabolisme vivant.
I'm a Canadian architect and designer who works in a collaboration associated with the University of Waterloo School of Architecture and in an art studio. We work in several layers combining computation, industrial design, architectural design, chemistry, and we put those things together in order to make a deeply layered, diffusive kind of nearly living architecture. Yeah.
Do you want to talk a little bit about the series, because it's part of the Isoloic Ground series? So do you want to talk about perhaps the different steps you evolved in that series to reach Radiant Soil?
Radiant Soil is a new generation of work that has occurred in a series for several years. And the name of that series is the Hylozoic series. Hylozoic means life coming out of material. It's a word taken from the Greek. And in this case, we mean it in several ways. In the hunger and the hope, perhaps, of the whole project, but also in the sense that we're working with materials that start to work generatively, that work in autocatalytic loops, that in some ways start to take care of themselves and interact through different tribal behaviors. And so things really are starting to get going and start to approach definitions of life. In the work that we're standing in here, we can see first generations of drawings that we make in order to control and compose the compositions. We're looking at some plans here, and then later on down the row you can see different assembly drawings. These are based on individual profiles, two-dimensional drawings, which we make in order to control digital fabrication. All of the work that we see here is custom in the sense that we make cutting profiles and then drive the machines that manufacture the elements. And then we hand assemble them. We use some simple machinery sometimes to automate that process. And then we prefabricate. We make clusters using large teams, and then we pack them tightly together, ship them, and then we open them up into space like the space we're in. And then we go to work in the final assembly, such as the huge team of volunteers that's been so generous here. So here you can see the kind of tribal clusters of different species of elements, which are all fitting together using this hexagonal geometry, a very efficient kind of space packing system that allows us to work very flexibly. Density of elements and the different behaviors of elements allows an interactive system which is layered and which will make quite a diffusive cloud when we erect it in a space. You can see that underlying it is a universal geometry system, and then this gets translated into relatively detailed individual assemblies, which are made of both structure and embedded computation, a bit of chemistry, glasswork, and textile-like principles to allow a resilient kind of organization to put it all together.
I heard you earlier, you talked about crickets downstairs, and so because they could look like kind kind of vegetal, they could look like jellyfish. So do you look at a particular metaphor in the design language you're using in terms of all the custom-made shapes? You know, they're feathers, they're like birds. Is that something you're exploring, looking at kind of mimicking the animal world in some ways?
The question of whether this work is biomimetic is an interesting one. Right now we're looking at one of the filter clusters, which is housed around a protocell incubating flask, together with very high-powered light, shape memory, alloy powered breathing pores which flex, and then a capacitance sensing whisker here. And this then multiplies together to make a great felt work, which is a kinetic valving element, which together makes convective plumes of air, which pump and breathe throughout the space. If we touch here, then this will vibrate and give us a response.
Okay.
And then that will send a signal to a microprocessor, which will come back, and that will operate individual pores like this. And they're designed to be deliberately fragile and flexible, so that a tiny little amount of contraction in the shape memory is amplified through leverage, and then through laminar organization, and then through the diffusive frond organization of these profiles. And so this kind of organization through gravity provides a sense of kind of trembling, kind of resonant responses that I thoroughly enjoy. Now that kind of response is made out of extremely practical design principles, like the diffusive form wants to have as much exposing area as possible, and so it's deeply reticulated, making something very different than what, say, a snowball or a raindrop would do. Instead, it opens up like a snowflake and present a tremendous amount of exposing area. Natural selection does provide that kind of form language quite often. Think of a palm frond,
Yes,
for example,
yeah.
or the gill of a fish. And so this is following some of those same principles. It's not explicitly imitating something. This is not
But
a
it's
jellyfish.
inspired, no, but it's inspired by
there's
some of the mechanics found in nature.
There is a direct dialogue
Great.
with some of those operations, and then they're re-abstracted and brought into a new function.
And what is the role of the protocells? And can you explain a little bit what is a protocell?
Institute Curie, which helped us with the chemistry. So my dear colleague Rachel Armstrong has helped formulate this particular protocell. And we're looking at two solutions, copper sulfate and potassium ferric cyanide. In this kind of flask, we have two oils, diethyl phthalate and oleic acid or olive oil. And the purpose of that is to make a buffered solution which is very gentle, so that it's held, so that then what happens between the two elements is somehow in suspension, which means that in the same way that a protected environment like that in a geode, crystals can form that are very delicate in that suspension. This is equivalent to that. So perhaps like a fetus in a womb, or a generative system deep under the sea. So I'll just put in some copper sulfate right at the boundary layer. If you might want to come in close, I don't know, to create a vesicle. And I just go a little bit slow, so that rather than many bubbles of material, I'm growing one alone. And you have to navigate the surface tension. Okay, so that vesicle, or little sphere of liquid now. And notice how it's ovoid, because gravity is not influencing it too much. It's able to work mostly free from gravity in the density of the two materials. And now the potassium ferric cyanide, cyan means copper, so the copper in these two solutions is going to exchange, and we'll see an interesting osmotic reaction just beginning. So I'm injecting inside the other, and you'll see a bubble form first. And then if you go a little bit closer, you'll notice that a reaction starts to form. And that will rapidly start to move. Now what you can see now a copper felt is starting to form. Do you see that delicate little brown felt?
Yeah.
Now, what is happening now is that osmosis, it's starting to pump through that membrane, deposit the copper at the boundary, and then you'll see clear liquid emerge at the bottom. So there's a little loop. That will continue, and it will form these kind of very deeply reticulated forms because the pressure that's fueling the osmosis means that breaks in the felt work happen. And that actually allows more material to come through, which then creates precipitate, which then closes it up again and renews the pressure. So there's this loop of failure and opening, which creates the pumping. In the same way that a walnut or a brain acquires solidity through reticulation. So it's not actually mass, it's more the exposing surface, which is deeply, deeply multiplied in a fractal relation. Fractal meaning that there are single folds, and then each of those fold and then folds up and on top of that. What is this thing? It's just an inorganic process. And yet somehow it generates some more relationship, which perhaps is the beginning of an empathy with these things. Of course it's artificial. It's nothing. But then we are nothing. So this is really a sketch or a model of a way that something could work. In the future, the kind of delicate copper felts or mineral felts that we see here could make fibers and skins which could come out of the flask and instead clothe an environment, like a geotextile kind of earth surface. Right now, they're being housed in a very early stage, and they're being influenced by a big charge of light that comes out the top, the passage of air, which regulates. And so it's at a stage where it's suggesting a way of working. Now, when this is multiplied intensely, it makes a field so that we don't concentrate so much on the individual figure of this, but rather on the overall fabric.
Yeah, the whole metabolic system.
That's right. So here we have a set of breathing pores that make up the general breathing felt, the breathing membrane. And we can see the different whiskers that will vibrate when we touch them. Down here, we can see another species. So what we're looking at here is a helical array of quite powerful LED lights that then come down here and are chained together to a proximity sensor. And when I come close, then there'll be an immediate reflex here, which then will ripple up. And if I come close again, then it will reflex again. We can see that there's the action here. And this contains multiple ripples of response. Each one of these little lights is controlled by a shift register, which is a kind of microprocessing relay, together with an Arduino, which is a simple, very basic computer. These elements are all chained together, and so there's a whole cluster or a tribe of these, which then work as a colony, and then they are speaking in turn to the breathing pores, and then also to a setup of organic power. So it's several different systems that work all together to make up the regulating framework of the environment. These will hang quite high overhead and will make a kind of canopy that will track our motion and will respond to our own movements. There's a third system in addition to these liquid arrays and the breathing pores, which is this kind of system. We can look at one that's working right now over there. So this is an array to contribute internal power to the system, Carol.
Okay.
And what we can see here is clusters of little vinegar batteries. When you were a child, did you make a lemon clock?
The lemon batteries, okay, right.
Or a potato clock,
yes,
perhaps? So these are vinegar with aluminum and copper electrodes. Each one of those makes a tiny little bit.
Amounts with micro voltage.
These are chained together in series, and so the power builds because they're all working together. And then we're just on a test circle right now, but they are going to a capacitor chip, which is collecting that power, and then it will blink out every minute or two in order to form then a control voltage, a signal, which then goes to the microprocessor, which is listening for it.
Okay.
That in turn then will be fed back to these
the
arrays.
one we've just seen. Okay.
And the effect of this then is to have an internally generated off-grid not coming from external sources, but internally generated automatic motion akin to the signal that makes you breathe, or perhaps that makes your heart beat. An organic source that is not at all a regular, relentless mechanical thing, but rather a slightly convulsive fluttering that produces a curious sense of presence in the system. Now, this is not efficient power. We're not talking about photovoltaic arrays that can power a city. And yet, by working with microscopic voltages,
it's intimate power in a way.
We get a very interesting, different kind of quality.
And it shows that it doesn't, it takes very little to actually trigger a fairly spectacular effect as well.
That's right, exactly.
Yes. Yeah.
And we spoke earlier about a kind of deliberate fragility and a tipping point, and perhaps this is another example of the same thing, where intimacy is something that can be very effective. It's a different quality than trying to be, as powerful and tough as possible.
Great. Maybe one last question.
Sure. Yeah.
To help to conclude a bit.
Yeah.
What is your ambition for this series? You have been developing all these mechanisms and these principles for a while now, and every time they get more and more complex and intricate and really extraordinary engineering, really. What is your ultimate ambition for this work?
When I think about the ambition for this work, I could imagine it going in two directions. One would be strongly into reality.
Okay.
In the sense that these are early sketches of possibility that could speak quite literally about what a future environment can be. A building in the future can live and breathe and know about us and care about us and take care of itself. And perhaps we can have a sense of the environment around us as being somehow fertile, somehow viable. I mean, an utterly different sense of perhaps justified optimism than the sense that we are using up our time on Earth, which is such a dark feeling that captivates so many of us. How can it not affect us emotionally? That's one ambition, which is to say, these sketches mean business and we want to translate them into building systems. And so part of our work works that way. This is a first generation of a thermoformed mesh and a mechanically expanded mesh, which we've drawn freeform. We can see the pattern here, for example, of opposing slits, and we draw it, and then we expand it, and we make it, and this is a pretty strong building material, which is optimized because it follows a diagram of forces, which is strong enough to hold up a building. I'm pretty excited about that. Now, on one hand, we have that ambition, but on the other hand, the sense of deliberate fragility and of resonance, of harvesting information and harvesting energies and perhaps projecting out those energies as well, produces a sense of expanded sensitivity and perhaps an uncertainty about what our consciousness and what our physiology is, in the sense of a playful expansion and exchange, which is very different energy than speaking about us as a bounded being. I am Philip, please respect me. I want to be allowed to do something. This kind of very natural force. Well, it's the opposite of that. Perhaps it plays off the same quality of wanting to roll down a hill and get dizzy. But in the sense of creating sensitivity, perhaps it's an absolutely concrete, practical method of generating some new senses. Were the medieval painters that painted halos speaking about the same thing? I mean, our project is not religious, but perhaps there's a common ground in the sense of generating some things and creating material reality out of subtle phenomena. Now, this is a system that we developed together this past January, which was seen on the runway just recently. And it's kind of a three-dimensional lacework.
But that's not 3D printed, this one.
This is laser. This is individual pieces are laser cut, and you can see that there's opposing arrays of chevrons, which are bifurcations, which come down and then they cross and then they open and then you pick them up and then you pick them up again. So it creates a corrugation, but which is flexible in 2 dimensions.
And you've assembled it by hand.
And this is hand assembled.
Right.
So these elements are drawn and then we make them using our laser cutters, and then we assemble them. And this then becomes this is like Fortuny pleating.
Yes.
But it's, rather than just using flexible materials, it uses an interchange of both stiff, rigid materials, crystalline materials, and highly flexible materials. And the composite produces really very encouraging qualities. You know, the fact that you can...
And very durable.
You can be tough, and you can play with it, and, you know, so the way that this can work on the body then is a pretty strong thing. And
so
now,
amazing.
so here's... Now, so this is brand new, and then here's a new mesh, which is made out of again a silicone sheet, which then is forced into the corrugation. And then this is a further generation of it, and I'm rather excited about this one because this is a parametrically controlled sheet where there are control curves.
Yeah.
So I can push and pull this and freeform it. We can freeform it, and then we make it into corrugations again.
And again with the hard and soft material.
That's right.
Yeah.
So the performance of this, for it to have a coherent structure, but then for it to become radically light like this, it has kind of a life in it that I think, or a responsiveness anyway, which is pretty encouraging.
And are you using these in the piece as well, somewhere?
No, these are
studies.
studies.
Oh, it's a privilege to see these.
And then you can see that then we're looking at clothing that, you see. So if you imagine like a great feather cloak surrounding you, or perhaps it can be more aggressive, or perhaps a little darker in sensuality. I mean, all of these are just some notes.
I mean, these could have photocells as well. Then.
Exactly. This is a tough enough system so that this can be a fluid reticulum as well. I mean, if you imagine this as being kind of a grotto around the body, which gets much darker in energy. So I'm rather encouraged by this. I think that this could, like, it's relatively simple to start actuating this as well. If we want to,
yeah,
like,
it's lightweight, isn't it? So
it's extremely lightweight. So therefore, it would not take very much force to start to work with kinetics in this.
And they're just plugged in.
Simply. It certainly can be. So these are just absolutely, like, these were just made this week. So perhaps in the next generation.
In the next project.